experimental searches. Maybe I'll give Professor Suman Veri to start the session.
Thank you. So good morning, everyone, and welcome to the first session of this day. We'll have 3 talks in this session. So first talk is by Dr. Suchita Kulkarni from Austria. She'll be talking on dark matter theoretical status. Welcome, Dr. Kulkarni.
Thank you. Okay, can you hear me? At the back? Is it too loud? All right, very good. Okay, so I'm supposed to be giving the first talk after the conference dinner, which is always a bit of an interesting situation because those who are not there have enjoyed too much. Those who are here have still enjoyed and kind of sleepy. So I have a job which is interesting, which is to keep you awake for the next half an hour and still tell you something which is at least semi-important or semi-interesting in the context of dark matter community and what people are thinking about, okay? So in the spirit of keeping you alive, I'm going to try and teach you a few German words. I'm not a good German speaker, but I know a few of them which are very, very peculiar and which you will generally not find in the literature. So let's see how this goes and whether you learn a bit about dark matter, or if not, at least you'll get a few bit of German while the talk is going on. Okay, so I'm supposed to talk about the theoretical status of dark matter, and I'm not going to give you an introduction about, dark matter exists, we have evidences, because clearly you all know all about it, and you've heard about it through the conference and talks elsewhere. What I want to start with is a bit of an overview in terms of landscape of different dark matter ideas that are out there, and where we are in terms of the exploration of those ideas. And to give you a bit of a perspective about what has happened in the last 10 years or so in terms of thinking about different kinds of dark matter candidates. And after this slide, I'll focus on a very specific topic that should probably give you an idea of where the challenges and opportunities in going in this direction lies, okay? So what you see here is basically a plot from the SNOMAS report of Cosmic Frontier, which shows basically the mass of dark matter on the top, some kind of interaction strength, which is on purpose not specified because it is always a model-dependent quantity, so it is some interaction strength that is dependent on the model. And in this huge parameter space, you basically see different classes of dark matter theories being mapped out, or models being mapped out. Now, one thing you would see is that there is no clear distinction between different models, because that's one of the things we have realized in the last many years. You can morph one theory into another theory by changing parameters slightly ever so. So our usual way of thinking of, for example, WIMPs existing in a specific region and warm dark matter existing in a very specific region sort of is an arbitrary division. So people now more like to think about the parameter space of dark matter as one continuum where you can morph theories from one to the other. Down here, you also have things like secluded dark sector, where you have, like the standard model, you have a completely new dark sector, and phenomenology and things can happen within that sector, which may not be, influenced by the standard model dynamics, and a whole different kind of phenomenology can come out of it. So what you see here in particular is that there is also a lot of attention which is currently being given for very, very light dark matter candidates. And these are very interesting because when the particle becomes that light, at some point of time, the wavelength of this particle actually becomes larger than the size of the particle, and it no longer remains a particle. So down here, when the masses become very, very light, there's a new class of dark matter candidates which are coming up, which are called wave-like dark matter. And in this way, or in this regime, you have to rethink the whole treatment because you no longer have a definition of particle, and that's a whole different kind of challenge which is coming up, both for the experimental and for the theoretical community. Okay, so you see that the parameter space is very vast. You see that we have, for few regions here, small ones, we have explored them and we have sensitivity, but a large part of it is still empty, and upcoming searches will actually try to cover it as much as possible. So that's the wide context of where dark matter theory and experimental status is today. What I want to talk about is a very, very specific part of that parameter space. In particular, a parameter space that is somewhere here, down here, if you wish, which are dark sectors or extended scenarios where you have many, many particles in dark sector. And in particular, what I want to question is whether dark matter can be a composite particle rather than being elementary. An elementary dark matter is something we have seen or we have studied for a very, very long time. WIMPs, as we have known them, are mostly elementary as we have studied, but there is no reason why it could be. Take standard model QCD, pions are composite, so why could dark matter not be? So that's the question that I'm asking, that I find interesting. Mostly because I'm working on it, I find it interesting and I know about it, so I thought I'd talk about it, okay? So the question is, can dark matter be composite instead of elementary? What do I mean by that? Think about standard model QCD, okay? And forget about mass non-degenerate quarks. Keep all mass, quark masses the same. What do you have? You have some kind of quarks, let me call them dark quarks. You have some engaged fields, let me call them gluons. At some scale, which is some lambda dark, this theory confines. So in UV, you have quarks, you have gluons. In IR, that is in low energy, these quarks basically form bound states that give you pions, bromison, baryons, the whole spectrum. Again, take standard model QCD, put it in a dark sector, what you get is the kind of scenario that I'm thinking about. The interesting part of this story is, and what we should remember in thinking about this, is everything that happens in UV, the dynamics of the UV sector at high scale is related to the dynamics of the IR sector at low scale. And therefore, we have to keep two things in our mind all the time when we are thinking about these theories and studying them. Okay. So this is not the first time this question is being asked. Okay? Composite dark matter scenarios have been studied for a very, very long time, in particular in the context of composite Higgs scenarios. So in that case, all the composite Higgs theories that were studied basically wanted to have a Higgs boson that was a composite particle, like the pion, and the dark matter would come out of one of the composite resonances which were heavier than the Higgs boson. That was the typical landscape of the theories. So this particularly gave a scale to the theory where the dark matter was always heavier than the Higgs boson, which meant that you couldn't get very, very light dark matter particles unless you tried very hard to construct such theories. So this problem sort of has been studied back from 1970s or so, and a lot of conclusions exist in terms of what kind of things are possible or not. What I want to do in particular is I want to decouple the two scales. I do not care whether a composite theory gives me a composite Higgs or not. And once the two scales are decoupled, all of a sudden a completely new landscape opens, and you can have dark matter particles which are much, much lighter than hundreds of GeV, and then you can ask, oh, if this is a kind of a choice of the nature, what's going to, how are we going to search for it and study such scenarios? Now you would ask why? Why do you want to make your life complicated? And my first answer would be why not, right? I mean, if you want to do a completely generic exploration of possible theory spaces, then you should consider all possible alternatives, and considering those alternatives would mean also considering composite theories. So why not is a good enough reason, but let me try to convince you a bit. One of the things that we've sort of been looking at in dark matter is the idea of dark matter self-interaction, which particularly comes from our observations of bullet cluster and so on and so forth. And basically, these observations put a light on the dark matter self-interaction cross-section, which is of the order of barn per GeV. Now, for us particle physicists, that's a really, really large cross-section. It's hard to get these kinds of cross-sections from elementary theories. However, if you think about the QCD, standard model QCD in particular, so these are measurements of PP scattering, processes from different experiments at different center of mass energies, you would see that typically you get cross-sections which are in the same ballpark as what you would expect for the self-interaction cross-sections of dark matter. So it is a theory that is going to give you use self-interaction cross-sections which are large enough, which are compatible with the current limits, and therefore you have a space in order to construct a theory that is wide. What else can you do? Well, since we are talking about composite sectors, we all have studied QCD to some extent. We know that in a composite sector, in standard model QCD, for example, we have 4 pion interactions. These are pseudoscalar particles, so 4 pion vortex exist. So you get self-interaction cross-sections from pion scattering with pion. So in this particular case, pion is the dark matter candidate. But you also get relic density for free because we have 3 to 2 interactions which are sourced by what are called as Vesumino-Witten interactions. Okay, so these are anomalous interactions. We have seen them in standard model QCD. We have 2 kaons to 3 pion final state. So why would you not have 3 pion to 2 pion final state in a theory like this? So this was a work which was done by Hitoshi and Yonit and company, wherein they show that you can have very nice limits on the mass of the pion and the ratio of the pion to pion decay constant, which are basically on one hand dictated by the self-interaction cross-sections, and on the other hand, they are dictated by the 3 to 2 annihilation that will give you a relic density. Okay? I'll come back to this part a bit later in the talk, but that's the idea. The idea is you get everything from dark sector more or less for free, and that makes these theories even more minimal because now you can engineer what you like in basically doing these kinds of dynamics. It gets even more interesting because now you want to go and study these theories. If you think about standard model QCD, at LHC you get jets. So you think about dark QCD, at LHC you're going to get dark jets. So here is one particular simulation of an event display of a given strongly interacting theory. It doesn't matter the details. And you see here, for example, that the jets which are originating from collision point are all displaced in different directions. Typically, events like this are thrown out by LHC collaborations because they are junk and you think they're just misreconstructed or detector firing in a random direction. But no, these are genuine predictions of a theory. So now you have to go and look into what you would have thought of junk in a good old days. Okay, so it presents challenges for theory space and for experimental space, and it sort of demands us to think about more things. Okay, so these theories are interesting, but they are also difficult to construct. Okay, the primary thing you need to worry about is you need to have a dark matter candidate which is very, very long-lived. Because the one thing we know about dark matter is it exists, and if it exists, it has lived for a very, very long time. So how do you do that? Well, traditionally we have been imposing symmetries, right? R parity supersymmetry, Z2 in any particle theory that you have written down, so on and so forth. But in the case of strongly interacting theories, you can also use accidental symmetries. Baryon in standard model QCD is stable because baryon number is conserved to the best of our knowledge. Okay? So you can use a baryon number conservation and you can create a baryon in a dark sector which will become your dark matter candidate. Or you can basically engineer models to ensure the stability. So how do you do that? Let's take a simple theory where you have up and down quark. Think about standard model QCD with flavor. You get 3 pions out of it, right? NF square minus 1. If you charge these pions under some external Z prime, think about a U1Y link, you would get a pi 0, a pi plus, and a pi minus. And of course, you will get a splitting between pi 0 and pi minus that will break the symmetry. So now you have to stop the pi 0 from decaying because it's a singlet. So what's the easiest way the pi 0 is going to decay? Again, think about pion of a standard model. Pion goes to 2 photons, and the 2 photon final state typically decaying the pi 0, which means your dark matter will go away. So you want to forbid this decay, and in order to do that, you have to engineer your charges such that the decay is forbidden. In this case, Q square proportional to 1 is what the choice seems to be. If you don't understand this, it doesn't matter. The point is you can construct a theory such that the pions remain maximally stable. That's the point of the story. Now, the last point is if you want to do all this and you want to actually do calculations, you want to have a quantitative estimate from a genuinely non-perturbative theory. Things where you cannot calculate using your usual day-to-day perturbative quantum field theory approximations, you need something more than that. And now you think about this problem and you say, oida, what do you do with it? Now, that brings me to my first German word, Oida. What is Oida? Oida is a German, Bavarian, Austrian expression, which literally meant old dude, but it can pretty much be used in any sense. I have linked you a very nice YouTube video here. If you want, go and watch it. It's going to be fully entertaining, I promise you. Okay, so let's come back to physics. You said, well, it's a difficult problem. How do we solve it? Well, turns out that standard model QCD and lattice theorists have a lot of work done here for us, and we can use it in order to sort of make our life simple. You want to construct a theory of a strongly interacting dark matter, you can use the understanding of symmetries and symmetry breaking mechanism. That is something that every particle physicist does all the time. Okay? You can use lattice simulations in order to actually calculate the non-perturbative quantities. And you can also use things like chiral perturbation theory or some sort of effective field theory technique in order to do calculation, which models like, us who are non-lattice people can do and understand something out of it. What it can give you, I think I have explained to you, and I hope I have convinced you that it gives us a lot of new signature and new analysis and new directions to think about. But also another thing that I like is I want to know if it can give us new understanding of strongly interacting dynamics itself, because there are a lot of open questions that we still have. Now, you can do all of this in lattice, okay? It's going to take you forever, and you can do it, but for all practical purposes, we would probably use a perturbative analysis just because it's going to be less time consuming. Okay, so let me sort of explain to you a few different scenarios, and I'm going to go a little bit fast on this point, but the idea was to give you a big picture, and then the details, you can meet me anytime in coffee break or lunch break, and we can discuss. All right, so I have a new non-abelian sector. Doesn't matter what it is at the moment. I couple it to the standard model. How do I do that? The easiest thing I can do is I can use the mediator from a standard model. You know that the Higgs, the W, the Z, the photon of the mediators of the standard model. So why not just reuse them and construct a theory? So that's sort of the first kind of thing that one would try to do. People try to do that a lot, okay? So the first thing was, for example, you could use a gluon mediator, which is relevant if you have your dark sector quarks have standard model color charges. And these kinds of theories are very interesting but very challenging. And for example, people like Rohini have worked on it, and you can ask her for more details. I'm not going to go into more details of this. If these theories couple to photon, they give you very, very strong constraint, even in an effective theory approximation, because they generate all sorts of magnetic dipole charge or polarizability. And that pushes the mass of the dark matter up to 10 TeV or so. So that's not very interesting either. So one could try to look at the Higgs and couple it to the dark quarks, which will of course happen via a Yukawa interaction, and you can construct a theory like that. So a particular example that we looked at was NC = 4, so SUN, take standard model QCD, SU3, just increase the gauge group, SU4, and with 4 flavors, and this will contain a scalar barrier. Okay, standard model proton is a spin half particle with 3 quarks. You have 4 quarks, you're going to get a spin 0 particle. Okay, right. So in this case, your dark quarks will have a bit of a mass from the Higgs, a bit of a mass from the vector-like state, but the details are not very relevant. What comes out of it is basically a very, very strong constraint on the mass of dark matter and the dark matter coupling from its interaction with the Higgs. So the reason why you get couplings on the interaction with the Higgs is because this is dictated by the Higgs exchange at direct detection experiments. Okay? And again, this is a quantity that is calculated on lattice, because even in the case of WIMP scenarios, we do get form factors from lattice calculations. So in the case of composite scenarios, you can get form factors from lattice calculations. Okay? Down here, you have LHC constraints, because you can produce the pions in this theory by Drelian production at the LHC, and LHC has very, very strong constraints, very interestingly from standard model measurements, and that pushes the mass of dark matter to a very, very high. So what this basically means is if you are going to use standard model mediators, you again go back to the situation where you have very small couplings and very high masses, which is exactly opposite to where I started with. I want very, very light dark matter particles to make these theories interesting. Okay, so that means I should not use standard model mediators. That means I should use a new mediator to couple the dark vector to the standard model. So I'm going to try and use a Z prime, which is the very, very original example I started where I was explaining pi to gamma, gamma decay to you. Okay? So if you have new mediators where you have an SUN sector and introducing a Z prime, what you get out of it are these fantastic looking events at LHC, which are called jets. Right? So I showed you this very nice event display where you had tracks coming out of vertex which are going all over the place, and I told you that you're going to discard these events. So you're going to get these really, really nice things where you're going to produce the dark quarks by a Z prime Rayleigh production. These dark quarks are going to go parton shower and hadronization in the dark sector, and some of them are going to decay back to the standard model. And what you're going to get is a jet with a missing energy in the same direction. That's a very, very unusual situation. That's something that we've not thought about a lot. And that is one of the very, very active area of research for LHC experimentalists who are very, very actively looking for these things at the moment. Okay, so if you want to again do these kinds of things, you would need the mass of at least the pion and the rho meson to, you want to look for these at the LHC. And again, lattice theory comes to us for a rescue where you can actually fit the mass of the pion and the mass of the rho meson by using the calculations which are done for different gauge groups from lattice results. So it presents to you a very, very interesting interplay between constructing a theory scenario and using results from a very, very different community. Okay, so I told you about beyond the standard, so one gauge group, which is a copy of standard model QCD, take SU3, which is a MC equals 3 theory, and you increase the number of colors and you get different kinds of signatures. But you know that in terms of thinking about gauge theories, SUN is not the only gauge group that we know about. There are other gauge groups that you can think about and you can write your theories with. And they can potentially give you, again, very, very interesting things to work with. So what happens when you start thinking about SUN gauge group? Well, turns out you need a bit of what is called as Durchchiasm. Okay, so that's German word number 2 for you. What's a Durchchiasm? This is an extremely rural Austrian word that's used in a very, very small village in Austria. And basically that means it's a long and a tedious calculation. Okay, that's everything that the professors here can take home, because we all give Durchchiasms to our students all the time, which are long and tedious calculations. Students may not enjoy it, but these are very, very interesting and important results. Okay, good. So let's think about a different gauge group and a different theory. What happens? Forget about the technicality. The first thing that happens is if you change a gauge group, you get a very different number of pions for the same number of quarks. Okay? In the standard model, in SUN, we've always been told that you have NF square minus 1 number of pions. So you have 2 quarks, you get 3 pions. That's NF square minus 1. Okay? Turns out if you actually change the gauge group, you have different, what is called a symmetry breaking pattern. So you have different coset spaces where the number of broken generators are different. And this means that you can have, in this particular case, for an SP4 theory or SPN theory, which is a pseudo-real representation, if you have 2 fermions, you get 5 pions out of it. Which is very interesting because you don't have to actually have a lot of matter content in your theory to get a new interaction. You can add just very little number of particles and get a very, very different theory. So let's try to understand this a little bit with pictures, right? How is it going to work when you are coupling it to the Z prime? So this is the same picture we had started with. This is an SUN theory with 2 fermions. We couple it with the Z prime. We said, well, we have 1 pi 0 and a 2 pions which are charged. In the SPN theory, which is a different gauge group, we get 5 pions. We couple these 5 pions to Z prime. Turns out we get 3 neutral pions and 2 charged pions. Totally different world, a completely different kind of interaction. Okay? something that we have to think about hard and something that we have to sort of, construct in a very, very careful fashion. And that's the Durkheimian part of the story. Not only that, you have to do new lattice calculation because a lot of lattice calculations that we've done are used for SUN gauge group. So if you have a different gauge group, you need a different lattice calculation. So this is something we did for SPN theory in a mass non-degenerate scenario. And what we established basically is that there is only some extent of mass difference that you can deal with in terms of chiral perturbation theory, because after some point, your rho mesons actually become lighter than pions, and at that point, the chiral perturbation theory techniques are no longer valid. The details are again not very important. The take-home message for you is that if you are studying this theory and if you are using things like effective field theories, you better make sure that your effective field theories are applicable to the region in which you are using them. Okay? Good. So this was actually one of the first times where lattice calculations for mass non-degenerate cases are performed. Okay. You can now change the thing again slightly. You can look at real representation instead of a complex representation or a pseudo-real representation. In this case, things become even more interesting. You again add 2 fermions, and because of the breaking pattern and the Cosec spaces that you get, you effectively get 9 pions out of 2 quarks. Okay? So that's the interesting part of constructing these theories and understanding them. As you change the gauge group, as you change the representation, you get very, very different phenomenology of performance. Okay? So you get these 9 pions, and you can construct a theory. It preserves the stability. This is a work which is actually done in progress with my master students at the moment. The previous few things I talked about were works which we did with a PhD student once. There's a different problem that this particular theory presents, which is the 5-point interaction that I've been talking about since the beginning of the talk that generates the relic density actually is very, very difficult to write down in this theory, in this particular course set that we have been studying. Okay? This has a technical reason, but in physics terms, the story is as follows. When we have a UV theory and we look at it IR, which is just consider pions alone, we want to write down all effective interactions by just considering pions and not caring about what happens at high energies. Okay? If you want to do that, the theory has to satisfy certain conditions. In a group theory language, these are called homotopy equations of certain kinds. In this particular theory, these equations are not satisfied, which means you cannot write down effective interactions of pions by just considering low energy dynamics. The way you can do, or you can write these interactions down, is in fact considering the theory in high scale, compute the interactions at high scale, and translate them down to low energy dynamics. Okay? So this is basically, this was shown very nicely in some of these papers, and Joachim here actually used these papers to write down effective interactions in these kinds of theories. So this is an example for you where you basically need to understand this theory not only in one direction or the other, but really the full interplay from very, very high energy physics to low energy physics in order to write down meaningful interactions. Okay? So, Phase, the last German word for you. That means in conclusion, in balance. What does all this mean? What I wanted to show you, even if you did not sort of get the full details of the story, is that these theories are interesting, they're challenging, they contain something for everybody. It contains something for experimentalists, it contains something for dark matter theorists, and if you really want to take these theories seriously, you should basically analyze them from all possible angles and consider the compatibility or consider the fact that everything has to be consistent at all scales. And this can be done by analyzing the symmetries, by using lattice simulations, and by making sure that the effective theories that you're writing down at low energies are actually consistent and used in the region that they can be used. If you actually end up doing that, you would understand that these theories give you a very interesting thing in terms of cosmological signature, in terms of new dark matter analysis, in terms of experimental circuits. Okay? So I presented a few different examples in this context. I hope you got the message out of it, even if not the technical details, that doesn't matter. I tried to convince you that you have to engineer these theories. These don't hop out of the bag very quickly. But you have a very, very interesting way of understanding these theories and analyzing the phenomenology of them. So thank you very much, and I'm happy to answer your questions.
Thank you for a nice talk. Now, questions. Yes, please. Yes, go ahead.
Arrived at the barn per GeV number from the bullet cluster?
Oh, I think Jasjit is a much better person to answer that question than I am, because we've been talking about these things for the last few days, and he has been teaching me, right? So how I understand the story, and Jasjit should correct me if I go wrong there, but basically what you've seen is a separation between the gravitational mass of the system versus the visible mass of the system. And using this separation, you basically try to understand how the gas has, how the systems have passed through each other and what could have caused the separation. And that dynamics basically gives you upper limit on how much the dark matter should have interacted to keep the centers apart as much as they are.
I thought that was more about transparency. You are talking about dark matter cross-section.
Yes. So because the gravitational centers of the two systems are far away from each other, okay, so in this picture, for example, we have the blue gas, which basically represents the gravitational system of gravitational center of the two clusters which have passed through each other, and the red gas here, it basically sort of shows you the visible mass of the story. So how is it, what keeps the gravitational mass as far away as possible, while the visible mass, which has clearly gone under collision, has a much closer center to each other compared to the gravitational center, right? So if you understand how passage of interacting matter works with each other, then you know what would be the maximum interaction allowed to make the system dynamically as much as it is.
Okay, I get it. And what's supposed to be the collision energy in GeV?
These are non-relativistic systems. So typically you would take the velocity of the dark matter to be 30% the speed of light or something like that. So collision energy...
No, then your proton-proton example won't work.
Why?
It's too low cross-section compared to barn per GeV. It's at the level of millibarn per GeV.
Correct. So the point of the story... okay. What I wanted to motivate was that you get barn-like cross-sections from QCD-like theories. Remember, these are upper limits on the self-interaction cross-sections. So you don't have, you don't have to quite reach 1 pound per GeV, but as long as you're in the ballpark, you're still in a better shape than not. So you get barn-like cross-section, okay? Now there's another part of the story, which is in standard model, you get the kind of cross-sections you get because alpha S is the way it is. Your strong coupling constant is what it is, which dictates the scattering cross-sections of strong interactions in QCD. If you look at a different theory, which has different scale than lambda QCD, then alpha S could change at a given energy, which can increase or decrease the cross-section within the strong sector. So you have a lot of room to play, but basically, given the fact that QCD gives you barn-like cross-sections already, makes you think, can you engineer a theory that will give you a bit more or less? That's the point.
Yes, please.
Hi, Suchita.
Hi.
So I wanted to ask you about, so if I just have a simple-minded model with a scalar, let's say scalar dark matter, so how do I see experimentally the internal dynamics that you're talking about, means from a simple-minded scalar extension with...
Okay, so right, so now you want to know whether, assume you've observed a signal and now you want to know whether that is actually an elementary particle or a composite particle. Think about standard model again. How do you know a proton is a composite particle? You've radiated it with energies which are higher and higher until you probe the substructure of the theory.
That's right.
So that's basically what you would end up doing, where you would, once you find the particle, you would probe it to see whether there is a substructure of the story. And if there is a substructure, then you would probably think, oh, there's something more going on in the story than just an elementary particle. That would be the easiest thing.
Yeah, that's what I wanted to know. What kind of what will you probe it with?
What would I probe? Oh, few different things. Okay. Let's see if I get there. There you go. Okay. So what would I probe? For example, in the context of a collider experiment, would be I would take the same theory and I would bombard it with different interactions, different beams. Okay. At very, very low energies, I would get sort of effective theory. So then at intermediate energies, I would get hadronic resonances out of it. Again, think about standard model. You get ions at Na64, things like that, right? You don't get quarks out of it. At very high energies, you would get jets out of it. So you can, again, take the same theory, increase the energy of your collider, and see if you get different signals going from resonances to jets. That will tell you if the particle is elementary or composite. That would be one way of looking at it. Okay? You can look at it at direct detection, because in direct detection, since these theories are composite, these are Goldstone bosons, these are all derivative interactions. You would get momentum dependencies in direct detection experiments. So you can try to look for those and things like that. So there are different ways in which you can basically differentiate between elementary and composite dynamics.
We can talk about it later.
Sure.
I'm just thinking that since you have only one mediator, anyway, so we'll talk about it later.
I'll be happy.
We have time for one more question. Yes, please. Yes, please.
You said like you will have experimental signatures in colliders themselves, which basically we are rejecting as junk. So what kind of experimental signatures are there, which we are basically not selecting or not triggering on?
Okay. So one of the signatures, the exact nature of your signature would depend on the theory. Okay. But what basically ends up happening is you get a dynamics which is a bit more complicated than standard model. Okay, let's think about standard model. You have LHC, you have collision of two protons that gives you two quarks. These two quarks rapidly parton shower and hadronize. That's why you see mesons, you don't see quarks at the end of the day. So, and that gives you jets, which is collimated spray of a particle, of number of particles in a given direction. Okay? In these kinds of theories, what you would have is very, very similar structure where you have dark quarks which are produced. They will parton shower and hadronize inside the dark sector. So the jets they will produce will be completely invisible at that time because these are completely dark jets. But some of these dark particles can decay back to the standard model. So now you have missing energy, and at the same time you have visible energy. Everything goes in the same direction.
So you will have a jet and missing ET imbalance.
In the same direction.
In the same direction.
In the same direction.
Okay.
And those are kind of things that we have not been looking for. Semi-visible jets, yes, correct. So we've not been looking for those kinds of things. You could get things with the... Now,
So what she is talking about, we are indeed looking for semi-visible jets, at least in CMS experiment, and there is already a published paper actually
absolutely,
on that.
but we've not been looking for it. This is a 2-year-old research,
Right, exactly.
So this is a very, very new thing, which is just being fired up right now as we speak. And then there are other kinds of things with jets with displaced vortices inside it and stuff like that. Just totally different things than what we have been searching for up to now in the context of new physics at the LHC.
Let's thank the speaker, and rest discussion can be on T. Thank you very much. Thank you, Sujit. So we have the next talk by Dr. Prateek Majumdar on dark matter experimental searches. Prateek Majumdar, please.
Hello? Yeah, I guess you can all hear me. So let me first start by thanking the organizers for inviting me to give this review talk on experimental searches for dark matter. And it's almost an impossible job to review all the experimental searches. That, as you will see in the next couple of slides, the number of experimental techniques and the methods that are being used in various experiments is almost mind-boggling. And so it's almost an impossible job to do that, but I will try to pick and choose a few areas interesting results have come up in the last few years, both in direct and indirect searches for dark matter. And so let me go on. I think the stage has been set by the previous speaker very well, that I don't need to spend any time on this, that there is quite an overwhelming evidence from astrophysical observations that there is existence for dark matter in our universe from all sorts of scales, from local scales, from galaxy clusters, and the universe, from cosmic microwave background, and many other cases. And this has also been stated that there are a plethora of dark matter candidates now. Most of us, we have been till now that the weakly interacting massive particles are the perfect candidates, are the best possible or the most suitable candidates, and people have been focusing on them for the last several years, almost a couple of 2 or 3 decades almost. One interesting thing which I would like to point out here is the way it started, how the field has grown from, let's say, the start of the 21st century, and over the years, the total number of different types of experiments that have come up, and how it has, and the number of researchers that have gone up in the field. So that tells you that this is a very, very interesting field, and something which is one of the most important areas of particle astrophysics or particle physics. Also, at the same time, how people have been improving the sensitivities of each of these detectors, each of these experimental techniques over the years. And you can see over the last 20, 30 years, people have been improving quite a significant way the sensitivities in order to search for dark matter. Now, the direct detection techniques, most of you know all this, but just to kind of review it, that it depends upon that you have a detector material, you have, let's say, a dark matter particle, your favorite candidate, maybe a WIMP, which scatters the nucleus of the nucleus of the detector material, and what you measure is the recoil energy of this nuclear recoil energy. It can be of different formats. It can be in the form of light. It can be in the form of charge. It can be in the form of heat. And then the different experimental experiments, I'll come to a few of them, which look for different signatures in it. What you basically do is that you are looking for an excess of events over a large number of background, because many other things can come and give you all these things, either the light or charge or heat. You would, for either the nuclear recoils, you can also look for electronic recoils, and then you can look at different ranges of masses depending upon what is the threshold of the recoil energy that you are operating at. Whether you are at keV energies, whether you are sub-keV energies, or whether you are at even electron volt energies. And that would kind of infer what sort of dark matter masses you are looking at. You can also look at something which is spin-independent or spin-dependent interactions, and you need to have different types of materials to probe that. The biggest challenge in all these experiments has been that the signal is really rare. You need large exposures, and you need very, very low background. You also need to go deep underground. And then there are other types of experiments which have actually created the most controversial results, is that you look for distinctive dark matter signatures in the annual modulation rate, in the interaction rate. And then there are also experiments which try to find out the direction of So, and here I show you, it's again a kind of a repetitive slide, but here, this, I would like you to concentrate on just this part of the slide, where you see all the types of experiments and the targeted materials, the different types of techniques that have been used all these years for detecting dark matter. And I easily understand that how difficult. Sorry for that. And you can easily understand how difficult it is to make a review out of all these things. Okay, so as I said, that the most controversial result came from the annual modulation rate of the dark matter. Yeah, so you know that as the sun goes through the disk of our Milky Way, and there is there is a relative velocity between the detector, your detector, and the sun, you would actually see a modulation in the event rate, in the event rate. You can also look at the track direction of the nuclear recoil, which could be used to distinguish a dark matter signal from the background events which you expect to be uniformly distributed. However, the biggest challenge is to reconstruct this track, which is very, very small, which is just a few millimeters in gas, and in solids it's even lower for energies of about, recoil energies about kilo electron volt. So the DAMA experiment in 2 phases used sodium iodide crystals and then thallium doped sodium iodide crystals in their another phase, and have seen and have reported about, in 2 phases, almost about more than 10 sigma in significance about the presence of dark matter, of a modulation with proper features. That was one of the latest results, with a huge detected ton per year, almost 3 ton per year, 3 ton year data. However, there were other experiments which have been built during the same time, which have not seen any modulation in their data. You would note that all these experiments were using different techniques. So it became almost important that the same experiment be repeated by other groups. So use sodium iodide, thallium doped things by others. And this was done in the Yang laboratory, the cosine collaboration, the cosine 100 collaboration, which is a combined collaboration of the dark matter ICE group and the KIMS experiment, the original Korea invisible mass search experiment. They came together and they used these sodium iodide thallium crystals, about 106 kgs, and they immersed it in the liquid scintillator and then run this experiment since 2016 for over now almost like 5-6 years, and they have put very, very strong constraints on the dark matter interpretation of the Gamma Libra signal, except the only small area which they cannot completely rule out is the very, very low mass region at around 10 GeV or so. Similar constraints have also been derived from the annual modulation rate experiment in the underground laboratory in Spain, and they have also their results have also been in very strong tension with the results which come from Gamma and Libra. So this has been the most controversial thing over the last few years. This thing is still not settled, and cosine experiment is actually improving their detectors, and hopefully in the next few years there will be more results coming up from that. Now let me comment, before I go on to other types of techniques very quickly, let me comment on what are the problems of an annual modulation search. These results rely on signal rates only. So the most analyses do not distinguish between the different signal types. You don't know whether they are nuclear recoils or whether they are electronic recoils there. Most electronic recoil events of these experiments are coming from radioactive backgrounds. So you really need to do radio pure crystals, and that's a very, very big challenge. How pure your crystals. And then no claim will be valid without fully understanding your background, and that's what the need is. You understand your background very, very well. So you need experiments with the capability to distinguish between these things, to detect WIMPs. And the technology which has been done, various other technologies, there are these 4 or 5, let's say bubble chambers, there are cryogenic bolometers, there's liquid argon or xenon, and and along with 2 phase time projection chambers, and I'll just go through them very quickly, one or two of them. The last decade, in my opinion, has been the era of the liquid xenon or the liquid argon detectors. What you do here, that you have in gas, these dark matter hits, let's say, a xenon atom. They put more xenon to make, they produce atom recoils and excites others, causing a light flash. That's the first light flash you see. They can also free electrons which travel upwards, and in the presence of an applied electric field, they can excite more xenon to make another light flash. So there will be 2 types of light flash, and which you can catch with your detectors. You can use then, these 2 light flashes have different pulse shapes. So you can actually use pulse shapes to reject your electron recoils. And the first results were the xenon and the xenon 1 ton, which has an active target of about 2,000 kilogram. And then the similar technology was followed using dark side, the 50, and they had an exposure of about 532 live days, and they produced some of the best results currently in vogue in producing in the limits on the cross sections of interaction cross sections. So here you see some of their results in the last few years. They had seen a few very interesting events at the low thresholds at around few keV, below 5 keV in their first data. However, when they started putting in more data over the years, they kind of understood that the excess, with the interesting excess which comes up, is probably contaminated by tritium. This is hydrogen 3 there. And they can give you the best spin-independent limit with argon. The argon detectors have given the spin-independent limit with around 10 to the power of minus 45 centimeters squared for 100 GeV WIMS. The plan for xenon is that now they have gone from 1 ton to several tons. Currently, they are taking data with a xenon target of about 6 tons, and they have been reducing their background. You see, when they started off in 15 years ago, 15 or 20 years ago, how much background they had. I'm sorry, this slide, the color of this slide is not so good, but I can understand that they have been reducing their background over the years, and now they are quite low, and they are quite efficient now. And so in the next years, within the next 4 or 5 years, we would have some very interesting results coming out from the xenon. We move on to the bubble chamber technology, where people use target liquids in metastable superheated states, and then they become sufficiently dense energy depositions, start the formation of bubbles, and then these are read by various cameras which you put around this bubble chamber. The most important collaboration which works on this sort of technique is the PICO collaboration, which has merged from the original Picasso and the Coop collaborations, and they operate their detectors as SNOLAB. And here is a kind of a timeline of how they had started their work, and now the present is that the PICO is about the PICO 40 liter, which is kind of taking data since a few years, and they have now, I think, got up to 60. This is a 60 kilogram, 50 kilogram of C3F8 the reason to use this kind of liquid states is that fluorine has an unpaired proton. For that, you would also be able to not only to do the spin-independent study, but also to do the spin-dependent study using these kind of detectors. So that's how they get some of the best spin-dependent WIM proton cross-section limits here. The PICO 60, that's a little bit of more details about here, because Shah Institute of Nuclear Physics is involved in this experiment, and so that's why I spend a little 1 or 2 more minutes on this bubble chamber technology. And as I said, they have very good electron recoil and alpha rejection there. They have, right now they are at around the 3 keV, 2.5 keV threshold, about more than 1,400 kilogram day exposure. And they have, as I said, they have given some of the most stringent spin-dependent WIM proton limits in this area. Moving on to the bolometers, there are two main experiments which have been operating. The cryogenic detector experiment, which is the CDMS or the upgraded version of the super CDMS experiment at the Soudan Underground Laboratory, which basically measure heat. Now we are going to a different regime where you measure the phonons, the heat by slight temperature, tiny temperature increases as in the interactions. And these also experiments, as you can see, I'm not going through all the details of the results. Then there is the other experiment, which is called the CREST-3 experiment at Gran Sasso, where they used scintillating bolometers, calcium tungstate, and they have a very, very low energy threshold, about 30 electron volt, so they can get some of the very good limits of WIMP nucleon down to about a few hundred MeV regime. So if you put together all the results of these experiments, you see that very, very strong upper limits have been coming on from the different techniques here. And as you see, that the xenon is gives some of the best limits, but the rest of the others are there. There is also quite a few experiments which are trying to lower their energy threshold, go down, and all these experiments have very strong tension when you want to interpret the Dama and Libra annual modulation signal as dark matter, even after you assume very general halo interaction models. The next stage in the lower mass regime would be the PICO 500, which is in design stage. It has been fully funded, and with PICO 60, you are actually kind of attacking the few tens of GeV regime, slightly around 20 GeV, or with PICO 40 and PICO 60. And they will be pushing their energy, the mass range much lower down to few GeV range. So this is kind of the overall status of the low mass GeV scale dark matter search. You can see here that you are almost touching almost the 1 GeV range, and the future experiments like the super CDMS using silicon detectors or germanium detectors and the CREST-3, they would be probably, along with PICO, they would be probably kind of trying to push the limits down to 1 GeV mass range or even slightly below that. So all of these experiments, the improvements relies on how well you can really go and suppress your background with a reasonably large target mass. That's the whole game that has been going on. So in India, there has been also a very, very modest effort in trying to look for dark matter at underground laboratory in Jadugoda. It's called the Jadugoda Underground Science Laboratory, led by Saha Institute of Nuclear Physics, where the concept which is being put there is the very similar concept to what has been used in Picasso experiment, where the so it's basically the superheated liquid droplet detectors, which are being fabricated in Saha Institute, and in collaboration a little bit with the Variable Energy Cyclotron Center, who participate in building the DAQ and the FPGA-based electronics. And then there is also IISER, which participates in the super CDMS experiment, and then there are future plans for building experiments with scintillation crystals at the India-based Neutrino Observatory, if that comes up and when that comes up. Here you can see a kind of timeline of the Jadugoda experiment. We are at a very early stage, and we have very few exposure per kilogram days. However, over the next few years, you can go up to something about half the exposure what Picasso had done, let's say a few years ago. Half the exposure of Picasso in about few months time scale by the end of 2024 or so. And then there are plans. If this becomes successful, these prototype detectors become successful, there would be plans to extend it further. However, probably at a different place, because Jadugoda may not have enough space to get bigger and bigger detectors there. So let me move on to the next stage of the next part of the talk, which is on the indirect detection of dark matter. Again, here you have so many experiments looking at the annihilation products of standard particles, either in the photons or neutrinos or charged particles, antiprotons, and all sorts of things. You have the gamma ray detectors coming from Hess Magic, and Fermilat. Then there are neutrino detectors like Antares, IceCube, and the future ones like KM3Net. And then there are AMS experiments. I won't be able to review most of them. I'll just pick and choose again one or two and few or a couple of them. You know, I don't have to motivate you how you look for the gamma ray flux from annihilation, because you have the particle physics here. You know this is where your interactions goes in, the annihilation cross sections. This is where the dark matter distribution goes in, and then this is the astrophysical part, which is the most unknown part or the most difficult part to determine. I'll show you why difficult, and then you can compute what the gamma ray flux would be. You can also do not just the gamma ray, but these standard model particles would, you can do a multi-wavelength analysis of that, because the standard model particles would also produce synchrotron radiation, which would be sensitive in radio telescopes. And I'll again show you a couple of slides on that. And then these synchrotron would again upscatter these synchrotron photons, the charged particles, into inverse Compton, which can go into X-rays or even in low energy gamma ray regime. So in all this, the most enigmatic thing again in indirect detection came from the claim of the line-like feature in 130 GeV and the excess from the galactic center. However, this was a tentative gamma ray line, was reported many years ago. It's almost now 10 years that has been reported by various groups of people by analyzing the data from Fermilat. However, with a very careful 4-year data analysis of the Fermilat collaboration had yielded no signal, and they had put quite some strong limits on that. There have been also searches by the at high energies by the ground-based observatories like HESS, MAGIC, or HAWK, where they have also put very strong constraints on the mass of the dark matter at a few TeV radius, starting from about 1 TeV, and then people are now trying to connect the results from Fermi, which are at lower energies at few hundred GeV, into TeV regimes, and to get the full cross-section, upper limits on the full cross-section. And there are all, and then you know that there has been an excess of in GeV energy seen from the center of our galaxy. However, an analysis, very careful analysis, does not yield a signal in terms of dark matter annihilation. Even though there is an excess which can be interpreted as dark matter, probably the things that you can attribute it to, because you don't know many of these things well enough, are the cosmic ray source distributions, how do cosmic rays propagate, the distribution of the interstellar gas in the Milky Way, or even unresolved point sources in the center of your galaxy, which you have not yet been able to find. So one has to really look into the astrophysics far more carefully, and it's a much more challenging job there than just jump into and try to make a dark matter interpretation of it. One has to hold your breath a little bit here, because astrophysics is really a very, very big enigma there. It's a very busy region, the galactic center. However, much more cleaner systems are the dwarf spheroidal galaxies, where the mass to light, where you have a high mass to light ratio, so you can kind of think that these are probably good targets for dark matter observations, where the light content is much, much low. However, the problem there is that if you do not have enough stars in these type of systems, you cannot get a handle on the astrophysical parameter, the J factor, which I was showing you a couple of slides ago. That is, how do the distribution of the dark matter along the line of sight happen? So there it starts to become extremely model dependent, even though these are somewhat cleaner systems. So there has been a lot of combined analysis done on these dwarf spheroidal galaxies using data from Fermilat and data from the imaging atmospheric, ground-based imaging atmospheric Cherenkov telescopes. Many hours of data have yielded almost no signal, and there have been some strong limits being put. However, most of these limits at the lower energies tend to cut across the relic thermal cross-section, and as you go to higher energies, the sensitivity of these instruments are still not there to go and probe the relic cross-sections yet. And so we have quite a way to go here to go and cut across this region. There have been some recent interest in radio observations, which seem to start to give some good, interesting, and strong constraints in the low dark matter mass. And let me show you a slide on that. And on dwarf spheroidals, some interesting results have come up and analysis have been done using both the very large array and the GMRT, the low frequency radio observations from giant meter wave radio telescopes, and all the MWA telescope, the Murchison Wide Field Array radio observatory. And so here are some of the interesting limits at the low dark matter mass, which seem to be doing better than the results which come from Fermilab. However, again, it's an astrophysical area where there are many, many unknowns. That's especially we don't know well the magnetic fields of these objects. We do not know how particles diffuse in these objects. So the diffusion coefficient become very model dependent. So all these things have to come from other observations, and one needs to bring in other areas of expertise in order to find out whether things have been done carefully, and then the limits can be derived from that. So that brings to an interesting question. So here is a plot which I picked up from a review from an article by Ian, John Bickham, and et al., where they have compiled all the current results from indirect detection using cosmic microwave background, Fermi, and the charged particle experiments like the AMS, and they bring out the question, is really the WIMP now really going to be dead? And they show that the area of the WIMP, even though not dead, is really getting very, very squeezed. There is not a lot of room now for WIMP. And I must tell you that a majority of these efforts on the indirect detection in India and abroad have come primarily from the vast amount of data which is now publicly available. So you are kind of, if you have knowledge about the experiments, you can go and analyze this data. It is not a privilege of a few people anymore. It is now given out to the public so that they can go and look for it. And yeah, so there is not a lot of place where the WIMP can survive. However, there are still areas where in the future, and the TeV energy, especially using the Cherenkov telescope array, one can probe. There can be the radio observations from the low frequency radio observations, which are already taking data LOFR, and we have been looking into the LOFR data recently, and for sub-GeV dark matter, and then in future, the square kilometer array can also have some say on it. So, because of time, because of want of time, I did not have enough time to cover some of the aspects which I have not covered, and let me just point them out to just motivate some discussion later on, not maybe during the talks, but later on even outside. There are directional detectors where you can try to get the direction using low pressure gas targets, using multi-wire proportional counters, or the TPCs, the time projection chambers. Then there is an experiment which is being under proposal and being commissioning stage. It's a multi-site, multi-target gas-based detector to dark matter below the. They would kind of go and hit the neutrino floor, and they would try to look for even solar neutrinos using directionality measurements. Then there are novel technologies to explore new dark matter landscape with very well motivated candidates from the electron volt to GeV masses, and they have been trying to use, these are more in R&D stage, using advanced ultra-sensitive detectors based on various technologies. And there you need to bring in not just particle physicists or astroparticle physicists. This becomes more of an interdisciplinary area because you need to bring in probably even condensed matter physicists into play to build up these ultra-sensitive detectors. For example, there's kind of these diamond detectors, these high purity diamond crystals which can be grown in the labs, can be used with charge readouts, can be very sensitive to both nuclear and electron recoil from dark matter in the MEV scales. And that would really push you down to the very low mass regime. And this is kind of the expected results that can happen at very low mass scale using various types of these novel technologies. Several aspects which I have not covered in the indirect detection part is the very interesting, and again a very controversial 3.5 keV line-like spectra which had come up a few years ago. And so you see all these people had worked on that. However, There is also a very interesting proposition using dark matter velocity spectroscopy in order to look for such things by these authors. Then I have not really covered the dark matter search using neutrinos or other types of dark matter, which could be the axion-like dark matter. Here you see a kind of plot by using the combined ice cube infrared search for dark matter in the direction of our Milky Way. And then there have been also some very interesting ideas about super heavy dark matter from the excess events which ice cube sees at the very highest energies, the very high energy ice cube events, and using complementary limits from the high energy photon limits from the photons using Tibet and Hawk air shower arrays. And there have been some interesting discussions on that of super heavy dark matter. So let me conclude that I think I have given you a small glimpse of all the worldwide experimental effort ongoing in order to find and understand the nature of dark matter. And as I said, it's just a glimpse of what I could gather, and my own personal bias goes in this direction. As you can see, that the direct detection searches are extremely challenging, and the signal is really rare. And in a few years from now, the way the sensitivities have been pushed to the limit, I expect that within a few years from now, in the few tens of GeV regime, we would be going and hitting the neutrino floor in about 8 to 10 years. Not even that, maybe even. We don't know whether that would mean that the weakly interacting massive particle, the scenario was going to be dead or not, but I'll leave it for the theorists to discuss whether that would be dead or they are still alive. In India, we have started a very modest beginning. There is a small underground lab which has been developed at Jadugoda, and we have been conducting over the last couple of years a small experiment there based on superheated liquid droplet method. And but this lab can also host some other experiments, like some nuclear physics experiments have also been operated there. And in future, there is the possibility of expanding it to a different site if the prototype and everything goes well. And the indirect detection searches are improving the limits on the cross sections also. However, this is an area where there is still a long way to go, because we don't really understand the astrophysics of the sources well enough. We really need to understand that better. And I apologize, as I said, that I have not really covered many of the experiments like AMS2 or DAMPE, who has given because the situation has not changed from what we knew about a few years ago, even with the new experiment like DAMPE, because the electron-positron excess can be interpreted as, again, as a dark matter signal, but probably is, again, most importantly, it is due to the astrophysics of astrophysics. Then there are also endeavors undertaken to address low mass sub-GeV or even to the MeV scale dark matter. The field, as I said, starts to become extremely interdisciplinary in nature there. We need to form interdisciplinary groups in order to attack that. So I would leave you with that, and thank you very much for your attention.
Thank you, Pratik, for a very informative talk. Now open for questions. Yes, please, Bob. Okay.
So I just wanted to know what are the signatures of the dark matter in the gamma ray telescope like experiment, the TV gamma ray telescope like HES or MAGIC or
the TV gamma ray telescope. So yeah, so this is basically the plot. You see the TV gamma ray telescopes kind of probe the areas around 100 GeV and beyond. And then the Fermilat tries to probe below 100 GeV.
No,
and
I'm saying what are the, what I wanted to know, the signatures in the data that one looks for.
The significance.
Signature.
Oh, the signatures. It's basically photons. Photons coming from the annihilation. The high energy gamma ray photons that come from annihilation.
Yes. Bhavna.
Hello, back here. So I have a question. So in the direct detection scenario, So where you talk about this xenon one-ton experiment, so those bounds, are they valid only for elastic scattering? And if the answer is yes, then what do we do in case of inelastic scattering?
They are only valid for elastic scattering. There are experiments which have now been built in Fermilab, small scale experiments like the Sensei collaboration, where they use inelastic scattering, the methods of inelastic scattering, and then they read out it with charge coupled devices, using charge coupled devices. But these experiments are focused primarily at very low mass. The thresholds are at almost sub-electron volt regime. And there the inelastic scattering technology is used there. So this is still kind of a very novel idea which are in the R&D stage, and they have started to take data, but probably we would learn more about them in the future, how, what sort of limits they can really get from that.
Thanks.
Can I ask? Yes. Okay. So thank you for the talk. In the last summary slide, you mentioned that we are now slowly moving towards this neutrino flow, right?
Pardon, I couldn't.
In the summary slide, you mentioned that we are now slowly moving towards the neutrino flow, right? And we will really soon approach there. So now in India, since we are just beginning, so which direction should we go? Like there is solid detectors, there is liquid detectors. So is there any opinion? I mean, from you, I just want to hear.
Okay. So if you let me go back to this slide, which is probably the most important in this one. So if you look here, if you go beyond something around 10, 20 or beyond that, the experiments that you have, they are going to reach this part of the neutrino floor in about 8 to 10 years. So now, if you are beginning right now, in order to compete with, this is again coming from a very personal bias, so
sure,
other people may have other opinions. In order to compete with these groups is, I think, beyond the hope. So the area where you can only work on is really this area.
Low mass.
This is an area in the sub-GeV case or around a few GeV case is an area which is still quite open. There are still technologies which are being developed, so you have an option to collaborate and compete both. You can collaborate with some of the groups, and that is what to some extent the PICO experimental people in Shah Institute have tried to do. So they have initially for a decade collaborated with the PICO group, the Picasso group, developed part of the technology in-house, then taking the knowledge from them, and then tried to implement it. However, of course, this requires a lot of experimental people working on this. Most of you probably know that the total number of experimental astroparticle physicists in the country is fewer than the excess signals you see in xenon data. So you really need to build up a pool of experimentalists in order to do. Otherwise, again, in this sector also, we will not be able to compete, because the other groups have at least 50, 60 people, and here we are order of magnitude less.
Right. So what are you trying to say, that the Jadugora experiment which we have is actually focusing on the low?
The Jadugora experiment is focusing right now around the 10 GeV, right? 10 to 20 GeV, 10 to 20 GeV. But in order to really push that, you need bigger detectors, somewhat bigger detectors, which is basically like Pico 60. We are at we will be half of Picasso in about a few years' time, which is already ended in 2016. So even that is so challenging, but at least that's a beginning, kind of a modest beginning. And if you can build up a group and you can show that the prototyping has worked and everything, then you can think of expanding it and then going into a regime somewhere around. Then I would also suggest that smaller groups can work on these novel technologies, which I had very briefly mentioned, which can take you to sub-GeV ones. Because these are again areas where R&D is being done all over the world. They are not really finished products, and then experiments have not really gone ahead and started working on them. So this is an area where we can probably hope to compete a bit.
Thank you.
Last quick question, please. We are already over time.
So I had an in-principle question about neutrino floor.
Yeah.
So when the WIMP search hits neutrino floor, does it necessarily mean that you cannot find WIMPs there anymore?
No.
Or is it that you have to find out signals that distinguish between neutrino and WIMPs more carefully at that point?
Absolutely.
And there could be some good ideas that come up in which we can do that. So it's not that WIMP search is dead when you hit the neutrino.
That's absolutely, that point is very fair taken, well taken. It does not necessarily mean, also this neutrino floor is, you can push it down also, because this various ways you can try to push down the neutrino floor also. As I mentioned, that the directionality of dark matter then becomes an important aspect there. So if you can have some ingenious ideas to understand the directionality, which is still extremely difficult and not much effort has gone in there. There has been some effort gone in, but not a lot of effort has gone in. And this is an area where one can still try to get to. But to go to that regime for us is very difficult and very challenging, because we are not even anywhere in this scale right now.
I know there must be many questions, but they can discuss at tea time with you.
Sure.
Thank you very much for a very nice talk. So the last talk of this session is by S. Sharma ji. Recent updates on finite temperature and density QCD from lattice. Sharma ji, please.
First, I would like to begin by thanking the organizers for giving me this opportunity to present the results that have been coming out from lattice QC studies at finite temperature density. So, lattice studies have been built up for many years of efforts, and I would be only focusing on the recent results which have come out since the last DAE-BRNS HEP Symposium that occurred online mode. So many of the results are new, and of course I may not have covered everything, so I would like to apologize for that. So, why is understanding this QCD at finite temperature density so interesting? Because QCD interactions account for the origin of more than 99% of the visible matter in the universe. So all of that happened in the very first epoch of the universe, where it is believed that a QCD phase transition happened at about 10 microseconds immediately after the Big Bang. So this regime is interesting because now there will be next generation gravitational wave experiments, the cosmic explorer, the ground-based experiments, which will have much more sensitivity than the current gravitational wave detector, and which will also look for gravitational wave signals coming out from these kind of phase transitions. And understanding this phase transition lies at the core of understanding why we exist, because this is the one of the versions of the QCD phase diagram that I took from the website of CERN. So what happens is, at low temperatures you have a hadron gas, and when you increase the temperature, then it deconfines into color degrees of freedom, which is called the quark-gluon plasma phase. And I would like to tell you that this phase diagram is largely unknown from first principles. We only know this part of it very well from lattice studies, and those results are now established. We have taken the continuum limit, and it is very well established in this small regime of net baryon density. But when we go to higher regimes of baryon densities, we do not have any first principles calculations, and I will come to that in the later part of my talk. But these states of matter are interesting because they exist in the core of neutron stars, and in this phase diagram, the two mechanisms that drive all these phase transitions are deconfinement and chiral symmetry breaking. They are very different mechanisms. The chiral symmetry breaking causes the pions to be much lighter than all other hadrons, and deconfinement means at some temperature and densities you get from a color neutral hadronic phase to a colored phase of quark and gluon quasiparticles. And these two mechanisms are largely not well understood from first principles, in the sense that what mechanism drives them is still an open question, and even confinement is one of the Millennium Prize problems which we all are trying to understand. So what we know from lattice studies over all these years is lattice QCD studies show that there is a crossover transition from the hadronic phase to this quark-gluon plasma phase at small baryon densities. When we are at the regime at 0 baryon density, then we know this transition temperature. This crossover transition temperature is about 156 MeV and is known to about 1% accuracy. It's a very unprecedented accuracy with which we know this regime very well. However, here we do not have much ideas. Most of the assumptions most of the studies here are based on quantum field theories which have same symmetries as QCD, which tell that there may be a first order phase transition at high densities. And so by this fast order phase transition should end up somewhere at a critical endpoint, which is also one of the questions which lattice is also trying to ask for. Where is the location of the critical endpoint? So as I mentioned, the phase diagram of QCD is mainly driven by these two phenomena. One is the chiral symmetry and one confinement. So in our real world, the light quark masses are much lighter than the scale of QCD. So the 2 + 1 flavor QCD has this U2 cross U2 symmetry, and it restricts it to a very good extent. Now the non-singlet part of it, actually the SU2 axial part gets broken, and that at low temperatures, and that leads to chiral stability breaking and existence of very light ions. And as I mentioned, this happens through a smooth crossover transition, and the temperature is known to a very unprecedented accuracy. Now there is also the singlet part of this chiral symmetry group, which is anomalous due to quantum effects, but it is known from lattice studies, from model studies which has same symmetries as QCD, that these may affect the chiral phase transition as the light quark mass goes to 0. So the question is, there are these two parts of the chiral symmetry, the non-singlet and the singlet part, and whether these two get simultaneously restored. Because this temperature is for this non-singlet part, but we do not know about what happens to the singlet. So as I mentioned, this UA1 is not an exact symmetry because of quantum anomalies. So how to look for its signal? So one way is to look at the correlation functions of different quantum number channels. So for example, the pion, which is an isospin doublet, would become degenerate with a sigma correlation function when the chiral symmetry or the non-singlet part is restored. Whereas for the pion will be degenerate with this delta when this UA1 part is approximately restored. So by looking at different correlation functions of mesons with specific quantum numbers and looking at their degeneracies, one can answer the question whether some symmetries are effectively restored or not. So looking at this table, one can write this correlation functions. These chi's correspond to the integrated correlation function corresponding to these mesons. So the sigma and the delta meson correlation function, the integrated one, is related by this relation where this chi disconnected is the contribution from the disconnected piece that comes from calculation of these correlation functions. Similarly, for the quantum, for these axial particles, you have this chi5 disconnected that comes. Now, when chiral symmetry is restored, then one would expect that if I take this relation, then this chi5 disconnected should also be equal to the chi disconnected. And then this correlation, the difference between these integrated correlators of ion and delta should give us this 2 times this disconnected part of the chiral susceptibility. Now, in lattice, one gets a very good observation of this So one sees that when this is as a function of T by Tc, so when one goes to the chiral symmetry restored phase, then the chi pi minus chi delta, which actually is the signal for this singlet restoration, actually gives a very good agreement with the disconnected piece of the chiral part of the susceptibility. So this is seen in this plot, where this UA1 kind of this UA1 restoration is evident as we go to high temperatures, shown by this shown by this closed symbol. And the way you should interpret it is that when you go to larger and larger in tau, you are going closer and closer to the continuum limit. So the agreement becomes quite good. Now, recently there has been studies from this collaboration that in the chiral sector, actually this singlet and non-singlet part mixes quite strongly. And that is evident from both the connected and disconnected part of the chiral susceptibility. So this chiral susceptibility is an order parameter for this non-singlet part, but then these dotted lines are the contributions from the singlet part of it. And it is seen that in both of these connected and disconnected pieces, the singlet part is quite dominant. Now this is not surprising, because this is what I also showed in the earlier slide, that when chiral symmetry is restored, then this disconnected part of the non-singlet piece of chiral symmetry has contribution from the singlet part, very strong. In this one, usually if the singlet part contribution are small, then the connected piece is given by the chiral condensate mainly. But then this part is also quite strong, and this has been seen from the recent lattice study. So now the question is, what happens to this singlet part of the chiral symmetry when one goes to the limit when the quark masses are 0? Because at that point of time, the chiral symmetry is exact, and then one wants to look at what happens to this contribution. And what from the lattice studies, we could go to quark masses as low as these values. For example, the lowest point corresponds to a light quark mass, which is 80 times smaller than the strange quark mass. And we see that this observable has a dependence which is quadratic in the light quark mass. So, which points to the fact that when we scale it with the light quark mass, then this quantity has a constant piece which survives in the chiral limit. So, the next point is we know that when chiral symmetry is broken, then the pion is the pseudo Goldstone mode of the broken symmetry. So, do we understand how a pion behaves in a thermal medium? So, one can write the dispersion relation of pion in terms of this velocity of the pion quasi-particle. And if one studies the spectral functions, then one can get the pion velocity by looking at the residue of the spectral function. So, initial studies were done within the framework of chiral perturbation theory without taking into account the thermal modification of the pion pole. But recently, lattice studies have calculated this thermal spectral function for the pion, and then by fitting it to this ansatz, where one puts in a thermal width for the pion, one could see that the pion velocities are consistent with the chiral perturbation theory if a thermal width of 30 MeV is included in this case. So there is a considerable amount of thermal modification that happens even for the lightest particle in the hadronic phase. And moreover, there has been studies about the chiral condensate, which is the order parameter of this chiral phase transition, and that also changes by 16% when one goes from 0 temperature to 128 MeV. And this 128 MeV is like about less than 80% of the transition temperature. So already when the transition temperature is at 156 MeV. So already at these low temperatures, the order parameter for the chiral phase transition as well as the Goldstone mode show significant thermal modification. So to summarize this section on the chiral symmetry, the new results show that the pseudo-Goldstone mode, which arise due to the restoration of chiral symmetry, has noticeable thermal effects. And the role of anomalous part of chiral symmetry, or the singlet part of it, is still not well understood, because one sees new surprises. And from these studies, it is important that in order to understand this hadronic phase, or the chiral symmetry broken phase, one needs to include finite temperature and density effects. So one needs to study these hadron spectral functions or the screening correlators at finite temperature and density to understand more what is happening in this hadron phase. Moreover, we have been only talking about the pseudo-Goldstone mode, whereas there is this non-Goldstone mode, which is the sigma field, which show very strong thermal dependence, and it still needs to be studied. What are these effects of the finite temperature and density on these pseudo-Goldstone modes, because ultimately they give us a clue of what will happen at the critical end. So, of course, as I showed you in the first slide, that the finite density regime is not very well addressed within lattice, because the conventional Monte Carlo techniques suffer from time problem. However, there are practical ways to circumvent it. So one of the ways, early ways, were developed in India from the TIFR group, and the way to circumvent it is to calculate thermodynamic quantities as zero baryon chemical potentials and expand in a Taylor series as a function of the baryon chemical potential. However, when one goes to lower temperatures, more closer to the critical point, then more closer to pseudo-critical point, then this convergence is very slow. So one needs effective ways to resum this series, and there has been a lot of new resummation schemes that has been discussed in the lattice literature for the last 2 years. And for a new resummation method, there has been a talk by Sabanya Mitra yesterday in the working group 5. You can see his talk. So all these resummation schemes now allow us to go to higher baryon density. So this is the measure of the trace anomaly, which is energy density minus the 3 times the pressure. So what happens to this quantity is that this quantity is shown for different baryon chemical potentials. So mu V by T goes from 1 to 3 as you go from bottom to top. So what at this yellow line corresponds to this chiral crossover line. So the line when chiral symmetry gets almost restored. And what one observes is that there is a significant enhancement happening to this quantity along the line of the chiral crossover transition. And it has been also observed that the energy density doesn't change so much along the lines of these crossover lines. However, if one wants to model QCD in terms of a non-interacting gas of hadrons and resonances, then the energy density changes significantly along this line. So, so interaction effects actually keep this energy density to be quite robust and constant along this line, even when one goes from 0 chemical potentials to a chemical potential about 2.52. Next quantity that is of interest is the speed of sound squared, which is shown in this figure. This has become very interesting because recent neutron star results. There has been reports that there are a recent discovery of a greater than 2 solar mass neutron star of a moderate radius. And to explain the equation of state of those neutron stars, one needs a speed of sound square which should go to greater than 1/3. So the lattice techniques cannot go to such high baryon densities. So here is a plot of the speed of sound squared as a function of on the lines of constant entropy by baryon density. So this gray band corresponds to 0 baryon density, and the interesting observation one gets is that when one goes to lower and lower ratios of this quantity, then one doesn't see a peak, doesn't see a minima at this region. So a minima is seen only for values of entropy by baryon density to be about 100. When one goes to lower and lower values, which corresponds to higher and higher baryon density regime, then the speed of sound square doesn't show a minima. And one can calculate within the hadron resonance gas model similar quantities, and it is if one looks at similar quantities at low temperatures at these values of entropy density by the number density, then one sees that in the hadron resonance gas model one sees a dip, and it is very difficult to reconcile this. So one needs better calculation and better ways to go to higher densities within the lattice cavity. Of course, there has been a lot of other methods to go to higher baryon densities, and they give consistent results with the Taylor series method. Now, the other thing is, as I showed in the first slides, that in the hadronic phase there has been significant thermal widths that these hadrons get even in this low temperature regime, and we do not much understand about the interactions. But of course, when we go to high densities, we expect we go to a more or less a perturbative regime. But do we understand the interactions, whether we immediately go to a phase of free colored particles or they are strongly interacting? So lattice studies has been ongoing in this direction. So one of the observables that people study in our community are the screening masses. So for any mesonic operator given by this set of, so this gamma can be for any choice of quantum numbers, then one can integrate over the two spatial dimension and also the Euclidean time dimension, and one can study this correlator as a function of one of the spatial directions. And for large distances, it should, to the leading order, it should go as the excitations would have the screening mass, or the correlation length goes as the inverse of the screening mass. So when one computes these screening masses, so the blue points correspond to the vector mesons, and the red points corresponds to the pseudoscalar meson, and this gray straight line corresponds to the expectation from a non-interacting quark, gluon plasma. So we see that there is a very significant deviation from the free quark gas, even at temperatures about 8 pg. And moreover, in leading order perturbation theory, one predicts that this vector and the pseudoscalar screening masses should become degenerate if perturbation theory holds good at NLO perturbation theory. But we see that even that is not true even at these high temperatures. So this tells us that this quark-gluon plasma phase is quite strongly interacting, and it is also evident in screening masses calculated for heavy bottom quarks. So if one looks at the difference between the screening masses of the vector minus the pseudoscalar in the bottomonium sector, one sees that for low temperatures about 300 to 400 MeV, the spin splitting between the vector and the pseudoscalar are consistent with the particle data group predictions. However, as one increases temperature, it deviates from the zero temperature prediction, so which tells us that it is acquiring large thermal widths. However, this is quite different from NLO perturbation theory. The same is true for the difference between the scalar and pseudoscalar screening masses. And by looking at the thermal dependence of these, one can get the deconfinement temperature of these quasi-particles in the medium. And this also points to the fact that the scalar and the pseudoscalar bottomonia melt at different temperatures. Now, what happens to the heavy quark in a quark-gluon plasma? So, if the heavy quarks masses are much larger than the largest scale present in the quark-gluon plasma, which is the temperature, then it is expected the heavy quarks undergo lunge-over dynamics, and this and the momenta of the heavy quark undergoes a spread inside the medium, and that is given by this heavy quark momentum diffusion coefficient. And this relaxation time is related to this heavy quark diffusion coefficient in this relation. And one can calculate this momentum diffusion coefficient in the limit when the masses of these heavy quarks are infinitely large from purely gluonic theories using gluonic color electric correlators. However, these calculations are tricky because the next to leading order corrections in perturbation theory are twice as large as the leading order. So one needs lattice calculations to calculate them. And recently in this year, there has been proposals to calculate this heavy quark momentum diffusion coefficient beyond the leading order or the infinite mass limit. So one has calculated this corrections which is of the order of mass by the temperature. So these are the plots of this coefficient, which is also the contribution of the magnetic color electric correlator from different groups, and they agree quite well at T greater than Tc or in the deconfined phase. And of course, there has been recent works to calculate the heavy quark momentum diffusion combining both the electric and the magnetic parts, and they show that they agree with the perturbation theory results only at very high temperatures, at about 10 or more than 10 times the crossover transition temperature. Below this, there are significant non-perturbative effects, which is captured in this different kind of bits that people use. And this C is actually giving us a measure of how much there is a departure from the NLO perturbation theory. And one sees a significant departure from even the NLO perturbation theory at high temperatures. So, given the time, I would not be able to cover this photon production rate. So, this is also another observable that actually tells us how strongly interacting the quark-gluon plasma is. And for the details of this talk, you can go to the talk by Dibyendu Bala at today at working group 5. So the observation that comes here is that if one calculates this heavy quark diffusion, this photon production rate is related to this quantity, and this also shows a significant deviation from perturbation theory predictions at large values of the momentum of the photon. So just to conclude, lattice QCD results continue to throw in many surprises, and recent results gives us new insights on the thermal modification of height hadrons in the chiral symmetry broken phase. So we are getting to understand the chiral symmetry broken phase in a much better manner. However, the mechanism that drives chiral symmetry or even the confinement is not very well understood. And also, latest results are now showing us that the high temperature phase or the quark-gluon plasma phase is far from being a perturbative medium. There are significant non-perturbative effects even at temperatures about 1 GeV. And this has interesting implications for transport properties and also eventual thermalization of the quark-gluon plasma. And we need now significant research for developing new lattice techniques to address fundamental questions in finite density QCD as well as non-equilibrium quantum field theory. So thank you very much.
Thank you. Thank you for your nice talk. So we are already exceeding the time. 1 or 2 quick questions if you have any. Yes, please.
Yeah, I just wanted a clarification. You were the previous one.
Oh.
The CS square you said goes greater than 1/3 somewhere.
No, it is in the neutron star observations. But here one cannot go to such large baryon density. So one can go up to higher baryon densities up to this ratio.
No, supposing you were to go in those larger density, in this plot, at what value of S over NB would it be going greater than 1/3?
Oh, that should be like about 10 or even lower.
And what is the problem in the box?
Oh, so it's not a problem, but it shows that after certain value of the entropy density, baryon number density, about 50, then it doesn't show a minima, but it actually shows a dip.
Suppose it doesn't show a minima, so what?
Yeah, so that tells us that here, for large densities, there is a probability that it may shoot up or it may have a different behavior than this kind of.
No, there is no contradiction of any kind if it doesn't go up.
No, there is no contradiction, but it is just that it doesn't show a dip here for larger barrier density.
Any other question? If not, let's thank the speaker once again. Organizers. 11:20 saying. 11:20 for the next session. Thank you. Thank you all for your patience.